Welcome, all you cool mathematicians. Now we're going to talk about section 7.4, where we discuss inverse trig functions. So we need to remember some stuff about inverses. The first thing we want to remember is that for an inverse to be a function, the original function must be one-to-one. So one-to-oneness is verified using the horizontal line test. All right, now the horizontal line test, if I were to draw a horizontal line through any of these functions, you should all notice that they are crossing at many spots, more than one spot. So the horizontal line test is very similar to the vertical line test. The vertical line test says that if we can draw a vertical line through a function and it crosses only once, no matter where I draw this vertical line, it would cross my sine or cosine or tangent function just once. So we know that they're all functions. If we draw a vertical line and it can only cross once, then it is a function. If it's possible for it to cross more than once, not a function. So the horizontal line test, like we just said, defines one-to-oneness. And none of these trig functions are one-to-one because every horizontal line I draw through crosses more than once. And if they're not one-to-one, that means the inverse is not a function. So what we do to create inverse trig functions that are indeed functions, right? We have to restrict the domain of these three basic trig functions. There are many different ways that we can restrict them, depending on the text. Different textbooks would maybe use different restrictions. But the three restrictions for sine, cosine, and tangent that we're going to discuss in this video, these are pretty standard. So what we're looking at here is the graph of sine. You see this gray curve that I've just outlined in blue, that represents my sine graph. And sine is not one-to-one, which means the inverse is not a function. So if we think about, what this means to find this inverse graph, well, that would mean taking those 5 key points for sine and switching x and y, right? So normally I'd have 0, 0, switch that 0, 1. Right here we would have pi over 2 up 1. Now that's going to be 1 pi over 2. Right here we would have pi 0, that would become 0 pi. And then we would have 3 pi over 2, negative 1, negative 1, 3 pi over 2, and 2 pi 0, which when we switch that x and y becomes 0, 2 pi. So these are points that create my sine inverse graph, right? Because remember, an inverse is switching the x and y values. That's really how we define an inverse. So 0, 0, over 1, up pi over 2, over 0, up pi, left 1, up 3 pi over 2, and over 0, up 2 pi. So you see that sine curve now moving vertically up my axis. Now, is this sine curve that I just drew in red, is this a function? And the answer is no, it's not a function because we cross more than once right there. All right, so how can we make this a function? How can we make this into something that we know is always going to work for our needs? So what we do, and we think about this graph is coming down here and continuing that curve, right? So we think about this inverse sine curve. I'm actually going to redraw it in light gray. So as we just sketched it, the sine looks like this when we reflect it over the identity y equals x. And the way we are going to restrict this is we are going to say that the range is from negative pi over 2 to positive pi over 2. So we'll only look at this portion of the curve. Right, so this is what we're going to want to know and keep memorized. So if we are dealing with y equals sine inverse of x, and that's the same as writing y equals arcsine of x. So moving towards Calc 2 or even Calc 3, where we are dealing with the negative ones a lot, we tend towards using arcsine instead of this sine -1 inverse notation. But they both mean the same thing. You might see calculators that would say arcsine instead of sine inverse. So the domain that we're going to use, these x values, are between -1 and 1, and the range, my y values, are going to be between negative pi over 2 and pi over 2. So what I've done here is I showed you how we developed this, and then I said, well, in order to make it a function, we're only going to consider this one little piece of the curve here. So that is my sine inverse graph. And what you need to know and store are this domain and range. All right, so let's talk about tangent and cosine as well. Here I have the graph of y equals cosine x. So my regular cosine graph looks like this. And if I take those 5 key points that are on our basic cosine graph and I find the inverse of them, those output values. So we start at 0, 1. That would give us 1, 0. This next point is normally at pi over 2, 0. So we have 0, pi over 2. My third point is normally at pi -1. That's going to become -1 pi. We've got 3 pi over 2, 0. Now that is 0, 3 pi over 2 when we switch the x and y. And the last one is 2 pi 1, which becomes 1, 2 pi. All right, so let me plot these. And, I've carefully rearranged my axes so that it works for us, graphing this way. We have over +1, 0, 0 pi over 2, -1 pi, 3 pi over 2, 0, and +1, 2 pi. So this represents the curve of my cosine graph. Wow, I could have drawn that a little bit better. More like this, right? It keeps going and it continues like this. Okay, so again, this cosine graph, what we have here, it's not 1 to 1. The inverse is not a function. So when we think about our y equals cosine inverse graph, or y equals arc cosine, the domain, well, you see my x values are all bounded between -1 and +1. But the way we restrict our range is slightly different here. We are going to have my y values go from 0 to pi. All right, so that range is that my y values are from 0 to pi. This is information you need stored about cosine inverse or the arc cosine graph. And the last thing that we're going to talk about here is our tangent inverse graph. So I'm not going to list and switch all of those points because I don't really think that's relevant. But if we think about reflecting this graph across the identity, what does that do to my curve? Now, remember, the tangent graph has vertical asymptotes at pi multiples of pi over 2. Right, so we've got these vertical asymptotes. And when I reflect a vertical line across the identity, those are going to become horizontal asymptotes. So we're going to have a horizontal asymptote at pi over 2 and negative pi over 2, and all of the pi multiples, pi distances away here. And so what my inverse cosine graph, if I wasn't restricting the domain and range, would look like, so I would have a graph that does this. Over and over again. But of course, this is not a function because it doesn't pass the vertical line test. So when we think about the graph of tangent inverse, we just use this one curve. So let's think about what the domain and range for tangent inverse or arctan are. We have y equals tangent inverse of x, or rather y equals arctan of x. So the domain for arctan, my x values are going to the left and the right forever. And the range, my y values are bounded between negative pi over 2 and positive pi over 2. Notice we can't touch those values. We are not going to touch these horizontal asymptotes. So unlike sine had the same range, or similar range, I should say, because sine had square brackets. We were allowed to equal those values. But with inverse tangent or arctan, we're not allowed to touch negative or positive pi over 2. So what you see here, these are my 3 standard graphs for arcsine, arccosine, and arctangent. And with them, I have listed the domains and ranges. These are things you need to know. So again, we have 3 inverse function graphs. We want to be familiar with their graph, but we need to know the domain and range for each of these 3 inverse trig function graphs. Store it. Figure out a way to remember it. I like to develop the picture and let you see what we're doing to create this, because I think that makes it maybe easier for you to remember. And this is really going to come into play, and this will start to make sense with some of the answers your calculator gets you. All right, so one last thing. Because we have these restrictions, when we start thinking about these inverse functions on the unit circle, we think about our solutions for arcsine. They're going to lie here between positive pi over 2 and negative pi over 2. We do not use quadrant 2 or quadrant 3 with arcsine. When we're dealing with arccosine or inverse cosine, we're only going to get answers between 0 and pi, or 0 and 180 degrees. So we don't use quadrant 3 and 4 with arccosine. And then arctangent, remember we have open circles here on these endpoints. So arctangent, we use the same region as arcsine, but knowing that we can't touch those boundaries at negative pi over 2 and pi over 2. So last thing here, connecting the concepts. What are we supposed to know? What are you as the students required to know in Miss Stein's class? I require you to know the domain and range for our three main trig functions, sine, cosine, and tangent. You're not required to have cosecant, secant, and cotangents, domains, and ranges stored in your brain, but you should be familiar with them. And then for our inverse functions, and it looks to me that cotangent inverse got cut off here. I'll go ahead and write that. That was all real, or negative infinity to positive infinity, and then we've got 0 to pi. But of course, I don't require you to know the three reciprocal functions. You just need to know tangent, cosine, and sine inverse. You need to know the domain and range for each of those. The reciprocal functions are just listed here for your knowledge. So now let's find function values. Let's think about how we can do this and do this without a calculator. So sine inverse of root 2 over 2. So normally we are given sine of theta is equal to some output y. But when we're dealing with inverse functions, we're saying, well, theta is sine inverse of that output. So essentially, this is asking us to find an angle measure where sine of theta equals root 2 over 2. Find theta when sine of theta equals root 2 over 2. And there are multiple spots on the unit circle, right? There are infinite coterminal angles. But in these problems, remember, we're only going to be considering, since we're dealing with sine inverse, the restricted range. So the restricted range for sine inverse is that we have those y values are between negative pi over 2 and positive pi over 2. So where, in which of these two quadrants, is sine equal to positive root 2 over 2? Now, if we went down here, this would be negative pi over 4. Going up this way, we would have positive pi over 4. That's where we get positive root 2 over 2, positive root 2 over 2. Notice in quadrant 4, we would have a negative sine value. So it's not quadrant 4, it's not negative pi over 4. The answer here is positive pi over 4. Even though you might say, well, Miss Stein, 9 pi over 4 is coterminal. 9 pi over 4 is the wrong answer. Your answer always has to fall within that restricted range for the inverse function. All right, let's look at another one. Let me erase a little of this so we have some more space. So now we've got cosine inverse of negative 1/2. So this is equal to an angle measure. Okay, remember we would say cosine theta equals y. So if we're dealing with an inverse function, theta is cosine inverse of that output y. So we want to find where is the output for cosine negative 1/2. If we think about our unit circle and we recall our restricted range, cosine is only defined, or cosine inverse, I should say, cosine inverse is only defined between 0 and pi. So even though there are two cosine values, And we know we've got pi over 3 has a 1/2 for cosine. We got 1/2 root 3 over 2, and 2 pi over 3 has a similar ordered pair, but that x value for cosine is negative. So in this situation, theta is going to equal 2 pi over 3. 2 pi over 3 is the solution and not any other coterminal angle. If you type this in your calculator in degree mode, if you go to degree mode on your calculator and type cosine inverse and then negative 0.5 or negative 1/2, if you're in degree mode, it's going to give you 120 degrees as the output. It's going to give you one answer. There's only one answer. It's not going to give you all of those other multiple coterminal angles. Okay, it's going to give you one answer. Now, when we start talking about solving problems and we use these inverse functions to solve for that angle value, in those situations, we may need to consider coterminal angles. But again, if we are presented with a problem like this, there is only one answer. There are not multiple answers. Okay, so if the inverse comes with it, you need to think about that inverse function range. So let's look at this last example here. Tangent inverse negative root 3 over 3. So we're going to do tangent inverse. Again, this means we're finding the angle. Thinking about this, tangent theta equals y, theta equals tangent inverse of y. Remember, tangent is an operation. When we move that operation to the other side of the equation, we're using inverse operations. All right, so we don't just divide by tangent. Tangent of theta. Now that's tangent inverse of y. What is my restricted range for tangent theta? And it's that those y values are not inclusive. We have an open interval from negative pi over 2 to positive pi over 2. So if we think about sketching this, we've got positive pi over 2, negative pi over 2. We disregard the other quadrants. So where does root 3 over 3 occur for tangent? Well, we have two spots to consider. I've got pi over 6, which gives me root 3 over 2 1/2, and negative pi over 6, which is root 3 over 2 negative 1/2. So for which of these will tangent be positive and tangent will be negative? And we know in quadrant 1, tangent's positive. In quadrant 4, my tangent values are negative. So my answer here is going to be negative pi over 6. Negative pi over 6. Again, if you type this into your calculator, if you were in degree mode, your calculator is going to give you out negative 30 degrees. It's not going to give you 11 pi over 6 or 5 pi over 6. It's only going to give you this one value. So like I said, if the inverse is given as part of the problem, there is only one acceptable angle output. And so I know this video got long. Thanks for hanging with me. As always, email me if you have any questions. In the next video, we're going to talk about compositions with inverse functions.